Welcome to Spring LIB.
In this exercise, we have a student who throws a rock horizontally with an initial speed of 18 meters per second off a cliff that has a height of 50 meters, and the rock falls in the direction of the water that's located below the cliff. In question A, we have to find what are the coordinates of the initial position of the rock. So in order to do that, first we need to set up a coordinate system, and I'm going to do it right here in green. So I'm going to choose the origin of the coordinate system as the point where the rock was thrown, with the y-coordinate pointing upwards and the x-coordinate to the right. And since the origin is exactly the point where the rock was thrown, then the initial position is just the origin, that is 0, 0. In question B, we have to find what are the coordinates of the initial velocity. So notice that the initial velocity, the initial velocity is horizontal because the rock was thrown horizontally. So there must only be a component in the x direction. So it's 18. All of the speed is in the x direction and nothing in the y direction. Okay. In question C, we have to say what is the appropriate model to work with the vertical motion of the rock. And notice that all along the trajectory of the rock, there is only the gravitational force acting downwards on the rock, and for that reason, the vertical acceleration, the vertical motion of the rock is the motion of a uniformly accelerated particle. Okay. In question D, we have to find what is the model, what should be the model that we have to work with for the horizontal motion of the particle. So notice that there are no forces acting horizontally on the rock, and for that reason, the motion will simply be a uniform one. So have the motion as a uniform motion, that is, with constant speed. In question E, we have to find symbolic equations for the components of the velocity v of the stone as a function of time. Okay, so this is vx, vy. And from the answers to question C and D, we have that the motion in the y-coordinate, in the x-coordinate, is the motion of a particle with constant speed. So this is just going to be the initial speed in the x direction, which we know is 18. And vy is the initial speed. Vy is the velocity of a particle that has a uniform acceleration. So this is VIY, that's the initial velocity in the y direction, minus GT. The minus is here because the acceleration is downwards. But remember that VI is 0, so VIY is 0, that is the y component of the initial velocity. So the y component of the velocity is just minus GT. Okay. So let me highlight the answers here. These two are the answers. In question F, we have to write symbolic equations for the position of the stone as a function of time. And we have that the position of a uniformly accelerated observer is given by y equals y0 plus v iy t plus the acceleration over 2 times the time squared. In our case, y0 is 0 and viy is 0, so y is equal to the acceleration, which is minus g, times t squared over 2. Okay, and for the x coordinate, the position of a uniform of a particle with a uniform speed, constant speed, is just x0 plus vix t. So x0 is 0, so x is just vix times t. Okay, so these two here are our answers. And now to the final two questions. In question G, we have to find how long does it take for the rock to reach the water after it was released. So all I'm going to do is to use the equation for the y-coordinate that I found in F. So we have that the y-coordinate when the y-coordinate when the rock reaches the water is minus 50, okay, because the height of the cliff is 50. So we have that y, which is minus 50, is equal to minus g, which is 9.8. Remember that everything here is just in the international system of units, so I'm not going to bother writing the units. So t is equal to the square root of 2 times 50 divided by 9.8. And this is equal to 3.19 seconds. Okay, and in question H, we have to find the speed and the angle with which the stone reaches the water. Okay, so the final speed, we can just go back to question E and see how the speed evolves with time. So notice that for the x-coordinate it's constant, for the y-coordinate it's minus gt. So Vx is just Vix, and that's 18 meters per second. And Vy is minus 9.8 times, which is g, times t, which is 3.19 s. So this is minus 31.3 meters per second. Okay, so the velocity is pointing in this direction. Suppose that this here is the x-axis, this here is the velocity. And we want to calculate the speed. Okay, the speed is just the square root, it's the module of the velocity, so it's the square root of vx squared plus vy squared. So this is the square root of 18 squared plus 31.3 squared, which is equal to 36.1 meters per second. And then we want to calculate the angle between the x-axis and the velocity. So actually what we want to do is calculate this angle here, phi. So in order to do that, I'm going to calculate theta and use the relation that phi plus theta equals 360. And then I can find theta. So notice that from the figure that the tangent of theta is equal to the module, the magnitude of Vy over the magnitude of Vx. So this is 31.3 divided by 18. Okay, so from here we have that this is equal to 1.739. And so the theta is, if we take the arctangent, 60.1 degrees. And for that reason, Phi, which is 360 minus 60.1, is equal to 299.9 degrees. Okay, and this is the angle with which the rock reaches the water. This concludes the exercise.